Okay, so this is the paired t-test week, paired t-test and correlation. So first, let's just get to the right directory and get our Excel and SPSS libraries loaded in. Okay, so the first was the weight loss example, and basically we were looking at the differences before and after of weight loss and then doing a paired t-test. We started off by doing a confidence interval. So this is just a manual confidence interval here using the QNorm function to get, we're going to do 99% confidence interval, QNorm alpha over 2, so from 0.01 to 0.99, so nothing we haven't done before. This is the confidence interval for the difference before and after weights, which agrees with what we did in class. The next example we're going to cover, we're going to just do the hypothesis test, the z-test. Remember, like SPSS, R does not generally like the single and two sample z-test, so we're going to do this manually. So basically, again, we're going to do alpha equals 0.01. If you recall, we did this test. Where are we? Here we are, the summer camp. So we were basically doing a one-tailed upper test. We found a very large z value because there was a big difference in weights. We objective c is greater than 2.33. And we also calculated a very large effect size. So let's go back to SPSS, sorry, to R. So alpha equals 0.01. Calculate the z-score, which was a very large z-score, 19.17. And here I just actually calculate the p-value. So again, we're trying to replicate SPSS. So we've got the p, it's a very large z-score, very small p-value, and reject if our p-value is less than the alpha. So that's obviously going to be true. Okay, so the other example we had is we had the salary example. So we were calculating this data here. We were basically pairing people up with similar characteristics. And again, we don't really go into things like propensity score matching in this class, but we just imagined we got the most similar males and females, i.e. this one might be, both might be accounting graduates with 3.3 GPAs, etc. And these were the starting salaries. So we did this in Excel, we did a paired t-test, and we also did a confidence interval. So what we were doing is when we did this in, so let's just read in the data. And so we got the male, the fit salaries, the female salaries, and the differences. When we did it in SPSS, we actually did a normality test. Just because we got a small sample here, we want to make sure it's normal. Again, I told you, there's a downside to these tests, and if you have a very small sample, it's very hard to prove something's not normal. The test has very low power. And again, with a large sample, very few things are truly normal. So this is the KS test, the Kolmogorov-Smirnov test. And we actually pass in the difference in salaries, which is we're assuming to be normal distributed. And what we had to do for this is we have to pass in the p-norm function. This is a general test, so it will work with any distribution. So we pass in the normal function, and we pass in the mean salary and the standard deviation salary. And then we find p-value 0.9942. So we don't have evidence that we have non-normality here. And we can also do the Shapiro-Wilk test. And this is actually just easier. We just pass in the differences. This is purely designed to test against the normal distribution. And again, p-value high, we don't have enough evidence that the data is non-normal. So then we actually do the match t-test. So we can do a t-test with passing the male salaries, passing the female salaries, And what we have to do in R is with the type of test, we're going to put paired equals true. So there's paired equals false, which is a default, which is the independent samples. We pass pair equals true. And we get a t-value of 2.9104, a p-value of 0.0173. And just let's remind ourselves of what we did. We used alpha equals 0.05, so this is going to be reject H0. And again, as I said, we can also do the one sample on the differences. So we're just going to run that test, and we get exactly the same result. T-value of 2.91 and a p-value of 0.0173, which is less than our testing alpha of 0.05. So in this instance, we reject. Okay, so the second part of this week was correlation. And I'm just going to kind of go through some ways of doing correlation in R. So the first example we did, this was the movie example. So we're just going to load in from the simple correlation example sheet with other movies. So let's just see what we got. And because of the weird way the spreadsheet was, it had lots of things in there. So I'm just going to pick the actual movie data, which is, so we have the tweet rate per hour and the revenue in millions. So use the core function in R for correlate, and we're just going to make sure we have the correct column names. These are a bit complicated. So tweet rate and revenue. We can calculate the correlation, which was 0.9078698. We get it in a table form. Any variable correlated with itself has a correlation of 1. And we can do a correlation test using core.test. And we get a t-value of 9.92 and a p-value very, very small. So we're going to reject the null hypothesis of zero correlation. And this matches what we did in class on the board, that we had a very significant result, rejecting the correlation. There's obviously a strong correlation between tweets per hour in the week before a movie is released and the actual movie revenue. Okay, so if you recall, we looked back at the IH&O data sets. We're just going to load this in from SPSS. And we're actually going to we could do a basic scatter plot, which is not particularly informative here. You can see we've basically got too many variables and we've not named the variables correctly. So this is just a bit of a mess. So we're going to use pairs.panels from the psych package to give us a better correlation table. And most importantly, we're actually only going to select 5 variables, and these are the variables that we actually utilized when we did it in class with SPSS. What else do we pass? PCH. This is just the shape of the dots. We're going to LM equals true. We're going to fit a regression model. We're going to give it confidence intervals, and stars just means we're going to give the significance of the correlations. So here we go. So you can see here, well, the nice thing about this is it actually shows the scatter plot. Because this is symmetric, we get the same correlation. For example, math quiz and heart rate pre and halfway pre and math quiz. We show the correlations on the top right, and we give the actual scatter plots on the bottom left with a regression line. And, you know, we have the stars. So 1 star is significant at alpha equals 0.05, 2 stars 0.01, and 3 stars 0.001. So we can see the heart rate pre and heart rate post is correlated. The 2 anxiety measures are correlated, but also heart rate pre has got some sort of correlation with the 2 anxiety measures. Let's just have a look what else we're doing. We could also plot a core table in R, which kind of gives exactly the same results. This is the basic correlation function in R with the COR. Now, to get a correlation table with significance values, we're going to use a library called HMIS. And we use the RCore function. And again, we're just passing and telling it we're doing a Pearson correlation, passing exactly the same variables. And here we get the first table is the correlations, then we get the N, and then we get the actual p-value. So that gives us more information. So we can do the same, but rather than this time, we're going to use Spearman. Complete observations just means that we only include where we have all the data in a row, which isn't a problem in this data, which isn't really a problem in this data set. We could also have it so we would have pairwise. So we'd actually, if we have two columns, we include any observation where we have values for both of those columns. So let's just do core table. This is for the Spearman. And again, HMIS gives us the Spearman correlations with the significances. So you can see here, this is a slightly higher negative correlation. We have the p-values, so math quiz and heart rate pre is significant, but math quiz and nothing else is significant. Heart rate pre, if we're setting alpha equals 0.05, its correlation with heart rate post is significant, and also the two anxiety measures. And then finally, let's just have a look. We had a partial correlation between heart rate post, math quiz 100, and heart rate pre, just saying that, you know, we should account for the heart rate before the exam, looking if there's a correlation between heart rate after the exam and your score on the quiz. So we're going to load in. We're just going to have in data, we're going to have these three columns. Heart rate post, math quiz 100, and heart rate pre. And we're now going to just do partial.r. And we're going to pass in our data. And here, this is the format. This is just saying we want the correlation between heart rate post and math quiz 100, the first two, accounting for heart rate pre. And here we go. We get the correlation, which is lowered between accounting for heart rate pre. The correlation between heart rate post and math quiz 100 is minus 0.06. Okay, so that's correlations in R at the end of the week 9 R material.